So we're going to look at the gravity model, which is part of traffic forecasting, and the main concept behind the gravity model, and it really is similar to, for instance, the gravitational pull between planets, and we're doing the same thing, but in this case we're looking at trips and trip producers and attractors and what the relationship is there. And the underlying assumption is that the likelihood that a trip occurs is a function of the distance and the trip attractiveness. And so that's what we're going to use this equation for. Of course, there's many more sophisticated models in traffic forecasting. This is a simplified model just looking at this one perspective, but there are lots of other things that we can consider if we're actually doing traffic forecasting. And so what we're going to do is we're going to solve for the total number of trips from TAZ-A to TAZ-B, and where TAZ is the traffic analysis zone. And so this is what we're going to use the equation for. So we're going to start with the total number of trips from TAZ-A. So how many trips does TAZ-A produce? And we're going to look at distributing it, and essentially we're going to weight this by the other zones and factors for the other zones. And those factors are the total number of trips attracted from TAZ-B, the distance or the travel cost, and this is also known as the friction factor. And a lot of times the value we use for that is 1 over the travel time from zone A to B. And then we have a socioeconomic factor, a parameter that is going to help us balance the results. And what it's doing is helping us measure the relationship and the likelihood between these two zones, A and B. So we're going to take a look at an example. We're told we should use the gravity model to estimate the number of trips between a university campus and zone 2 during the PM peak hour. The university campus is expected to generate 1,100 trips during the PM peak hour, and it will be distributed to these 3 traffic analysis zones. Of course, this is a very simplified example. In reality, this would be much more complex and labor intense, but we're just looking at a few zones here. So we have some data on each zone. We've got the travel time in minutes. We've got the number of trips attracted during a typical PM peak hour. That doesn't mean from our zone in particular. That's what these zones are attracting during the PM peak hour. And this is going to help us give us an idea of how it's going to influence how those 1,100 trips from our campus are going to be distributed. And then finally, there's a socioeconomic factor between the campus and each zone. And the higher that value is, the higher that factor is, the more relationship there is. And so, for instance, if we're thinking about it in the context of a university campus and how we're going to distribute those trips, those would be things like, are there affordable housing for college students? And so the higher that factor is, that's telling us there's a strong relationship between these two zones, campus and the zone, and that there's housing opportunities there, or there's attractions that they would want to travel to. And the lower values represent lower likelihood or lower relationship between those the campus and that zone.
So we're going to start by setting up our table here, 1 row for each zone. And we're going to start with our friction factor, F sub AB, so the friction factor between zones A and B. And as I mentioned, it's typically the inverse of the travel time. So for zone 1, it's 1 divided by 8, which gives us a friction factor of 0.125. And then the next one is 1 divided by 12, and then 1 divided by 17 for zones 2 and 3. For our attractions, this just the trips attracted to TAZ-B. This is our given, so 4,500 for zone 1, 2,200 for zone 2, and 3,600 for zone 3. Now we have our socioeconomic factor, and this is going to help us balance the results, and it also gives us the relationship between the 2 zones of interest. So the higher that socioeconomic factor, the more similarities there are, and the higher the likelihood that they're related. So for instance, this 1.8 in this example could mean that there's more housing for university students, and so there's more likely to have that connection, where zone 3 with the lowest number of the value of 0.6 means that there's less similar socioeconomic factors, so there's likely going to be less desire for travel between those zones. Our next column is to multiply those three values. So for the first row, we would multiply 0.125 times 4,500 times 1.8 to get a value of 1,012.5. We're going to need to sum up this column. We get a summation of 1,387.177. And then basically we're going to use this column and that total to distribute the trips, our 1,100 trips. So in this next column here, we're going to take each individual value from the previous column and divide by the total. So start with the first one, 1,012.5 divided by 1,387.177. And that's going to give us our value of 0.73. So again, we're going to take this value divided by 1,387, and that's going to give us 0.73. We'll do the same thing for the next row. This 0.15 is equal to 201.667 divided by 1,387.177. And this is telling us roughly that we're going to have 73% of the trips go to or attributed to zone 1, 15% in zone 2, and 12% attributed to zone 3. And that should sum up to 1. So again, those previous steps ultimately are just helping us apportion what amount is going to go or be attributed to each zone. And for our actual trips, we're going to multiply those percentages or those proportions by 1,100. So we'll have 803 for zone 1, 160 for zone 2, and 137 for zone 3. Our question actually asks us about the number of trips between the university campus and zone 2 during the PM peak hour, and this would be our 160 trips here, which is in our second row of the table. So our final answer is 160.